Welcome to the webinar Motor Control with Embedded Coder for Microchip MCUs. This is a partner webinar from MathWorks and Microchip. My name is Daniel Weider. I'm an application engineer at MathWorks focused on embedded code generation.
And my name is Christoph Baumgartner. I'm System Specialist FAE for Motor Control in Microchip.
Here you see the motor control evaluation board we will use during this webinar session. It is a motor control unit from Microchip targeted to control a brushless DC or permanent magnet synchronous motor. There's running a sensorless motor control application based on a Simulink model. The control design was done in Simulink with the help of closed-loop simulations. Optimized code for the Microchip 16 and 32-bit MCUs was generated directly out of this model using embedded coder and the MPLAB 16-bit device blocks for Simulink. Here you see the key takeaways of this webinar session. In our proposed workflow, the model is at the center. This means that the whole algorithm design is done in Simulink. Any changes in the development process have to be reflected in the model. Out of the model, we generate customized code for Microchip MCUs. And the algorithms which we designed in Simulink are directly tested on the Microchip MCU with real hardware using rapid prototyping. This is the agenda of today's webinar. In the first part, Christoph is going to present you the industry trends in motor control and the motor control solutions which Microchip can provide. In the second part, I'm going to present you an embedded system design process using model-based design with MATLAB Simulink and production code generation with embedded coder. In the last part, we are getting more detailed on the hardware demo we showed you in the beginning. So Christoph, why should I use Microchip MCUs in order to control my motor?
Thank you, Daniel. You definitely should consider Microchip for your motor control, because we are a leading provider of embedded solutions for this application area. In the next few minutes, I am going to explain you several reasons why you should consider Microchip. One of the main reasons for this is the continued quest for improved energy efficiency in all application markets. Some of that is a result of new energy efficiency regulations, but also the reduced operating cost that higher efficiency motors bring. This trend is also in lower cost applications like pumps and fans, and in battery operated products like power tools to extend the operating time. Of course, the need for higher performance on top of efficient drives, the need for more advanced algorithms that demand the performance of products like dsPIC and PIC32. Microchip's answer for this high-performance motor control algorithms is dsPIC digital signal controllers and PIC32 MCUs with enhanced DSP instructions to fulfill the requirements for speed and torque control, to do efficient field-oriented control and sensorless control. We have a lot of optimized peripherals and features that support motor control applications. Very flexible and high-resolution PWMs, intelligent high-speed A to D converters that are coupled with the PWM modules, integrated operational amplifiers and comparators for a high analog integration into a single device. We also have microcontrollers for dual motor control capabilities where we can run two motors out of one microcontroller, a lot of functional safety features and Class B libraries. We also have a very wide support of development tools, software algorithms for brushless DC motors, permanent magnet synchronous motors, AC induction motors, stepper motors, with a lot of support for different sensorless field-oriented control algorithms. So Microchip can help with energy savings. To incorporate field-oriented control, we have plenty of algorithms and software libraries available. Microchip can also help with noise reduction, incorporate sinusoidal control, field-oriented control, remove expensive sensors, and go sensorless. Our A to D converters support 4 sample and hold stages, so up to 4 signals can be measured in parallel. Microchip can help with cost reduction. Integrate controller on the motor in very small packages, 6 by 6 millimeters. Easily migrate in between the MCUs. We have a very wide portfolio that is hardware and software pin compatible. Remove the crystal and external analog products from your BOM. We have a very accurate internal RC oscillator, operational amplifiers, and comparators. Microchip can help with better torque control, incorporate field-oriented control, maximum torque per amp algorithms, and better loop response with our multiple sample and hold A to D converters. Microchip can help with improved reliability. Migrate from brushed to brushless motors, add Class B software classification libraries, and enhanced reliability support in hardware with ECC flash, CRC, and Deadman timer. Let's focus on the Microchip motor control development support based on our rapid prototyping tools around MATLAB and Simulink. The most important part are the MPLAB device blocks for Simulink. These blocks are the link between the Simulink model and the peripherals on the target microcontroller. So we have a lot of peripherals available, and on our webpage you can download a free version that supports up to 8 I/O pins on any of the microcontrollers. And don't worry, if you want to do motor control with our motor control development board, I will highlight later, this board is fully supported without any limitation. The peripheral blocks support many of the peripherals on the microcontroller. We have the analog to digital converter, we have the PWM supported, standard digital I/O pins, bus systems like UART, SPI, I2C, and some special functions to also include C function libraries into your model. Once you have your model completely simulated and you're happy with your simulation, you add the peripheral blocks to the control algorithm to make the connection of the model to the peripheral of the microcontroller. These peripheral blocks are generating code for your target microcontroller. They are doing all the initialization and runtime updates of the peripherals. Additionally, Microchip has also developed a motor control library for Simulink with all the standard functions for field-oriented control, all the transformations like Clark, Park, inverse Park, PI controllers, sine and cosine signals. These transformations we have implemented very efficiently to save calculation power on your target microcontroller to have enough room for your developments of the control algorithm. Also, these blocks are available for free on our webpage. Device families we target with MATLAB Simulink Rapid Prototype solutions are DSPIC33E. This is the actual workhorse in motor control. It's a 70 MIPS single cycle instruction DSC platform with improved PWM, features 12-bit A to D converter, a lot of op-amps and comparators included, and devices available up to 512 kilobytes of flash, also available in very small packages with a 5x5 millimeter. To give you a quick and easy start with Microchip and motor control developments, we can also support you with a variety of development boards. The low-end entry point is the motor control starter kit, which has the debugger and the motor directly included for low-end learning of Microchip and motor control. The most powerful low-voltage demo board is the MCLV2 board, which supports up to 3 phases for BLDC and PMSM motors, 48 volts and 15 amps, also with the CAN and the LIN and the UART interface. You can put a lot of different microcontrollers with plug-in modules onto the board. A very similar concept we have created with the DSPIC-DEM MCHV2. This is the high voltage variant of the MCLV2 board that supports 110 or 220 volt AC input and motor power up to 1 kilowatt. It also has an integrated PFC stage where you can use the same microcontroller for a fully digital PFC as well. The latest development board we have introduced is the Low Voltage Motor Control Development Bundle. It is a modular design. It separates the control and the power board, and it allows the customer to develop its own power board. This board supports dual motor drive, and it also supports our latest 5-volt DSPIC33 EV products. On the power stage, the Microchip automotive qualified companion chips are used, and we are also supporting them with our rapid prototyping solutions. Daniel, what's the part of MathWorks in this development environment?
Thank you, Christoph. MathWorks provides the tools to accelerate and improve the development process. Engineers developing motor control, battery management, and power conversion systems reduce their efforts by using MATLAB, Simulink, and model-based design. Customers report saving as much as 50% in overall development time, having fewer design iterations, and creating defect-free C code and HDL implementations during their first project. Using models in the development process helps you to have more precise specifications. Executable models as one truth are clearer and are not interpretable as textual specifications, as they show the dynamic behavior. Models can be simulated. This speeds up the design process. Many iterations can be done using simulation instead of real prototypes. Production code generation minimizes coding errors and is a reproducible workflow from the models which are derived from the requirements to the code. Continuous testing and verification helps to find errors earlier in the development process. Here you see a development process SV model, which is one example how a development process can be described. The benefits of model-based design, which we discussed in the slide before, can be applied during the whole development process, starting from the requirements over the system and software design, production code generation, integration, and calibration. The model can be used with the help of code generation to also do many steps of the development on hardware. The system design is verified to meet requirements using simulation. With rapid prototyping, the algorithm is directly validated with hardware. On-target prototyping uses the actual hardware and hence includes more specific hardware effects such as latencies. Processor-in-the-loop testing proves functional equivalence between model and executed code. Hardware-in-the-loop testing helps to use less expensive resources during integration and calibration. It furthermore can be used to test the system with any environment conditions. Here you see some of our customers which successfully are using model-based design. They reported development time savings between 40 and 75%. You can find further information in the user stories on our homepage. There are different kinds of coders. For C and C++, the MATLAB and Simulink coder are extended by embedded coder, which provides capabilities such as code optimization and verification, profiling, customization, support for embedded targets, and certification. All coders generate portable code by default, which means that the generated code can be used on any device. Executable specifications are more precise specifications. They are derived from the requirements captured in the requirement management tool as DOORS, Polarian, PCT Integrity, or also in Word. The executable specifications are derived from the requirements using different modeling tools, which are all included in the MATLAB Simulink toolchain. Block diagrams in Simulink are most suitable for all kinds of signal and control tasks. Plant modeling can be done with our physical modeling tools. They enhance Simulink with the capability to model physical systems implicit, such as electric motor, as electrical and mechanical system as shown in the slide. Stateflow is an environment for modeling and simulating combinatorial and sequential decision logic based on state machines and flowcharts. Furthermore, MATLAB can be used to model anything in textual form. All the modeling tools can be combined. This means that each part of the system can be modeled with the appropriate tool. Executable specification means that the models which we derived from requirements can be directly tested in simulation. This helps to find errors or missing requirements very early in the development process. With rapid prototyping, those executable specifications can be tested directly with hardware. This validates the algorithm and tests its feasibility with the real hardware. As models can be simulated, many design iterations can be done with simulation models instead of expensive real prototypes. This makes the overall design process faster and more flexible. For example, you can already work on the control design while waiting for the motor hardware. Hardware constraints can be reflected in the simulation. If the algorithm needs to run on a hardware without floating point unit, the conversion to fixed point can be done in simulation. Based on the simulation results, the appropriate bit lengths and best scaling can be found. The generation of production code directly out of the Simulink models minimizes coding errors and is a reproducible workflow from the models which are derived from the requirements. This helps you to implement sooner. Embedded Coder generates readable, compact and fast C and C++ code for use on embedded processors, on target rapid prototyping boards and microprocessors used in mass production. Embedded Coder enables additional MATLAB Coder and Simulink Coder configuration options and advanced optimizations for fine-grained control of the generated code's functions, files, and data. These optimizations improve code efficiency and facilitate integration with legacy code, data types, and calibration parameters used in production. You can incorporate the third-party development environment into the build process to produce an executable for turnkey deployment on your embedded system. Function interface specifications can be configured and validated. With the help of storage classes, the generated code can be customized to fit into the software project environment where it is glued into. Portable code can be generated directly out of the portable models. Processor-optimized code, which means target-specific code, can be generated out of the portable models just by adapting the code generation toolchain settings. The integration with the peripherals is provided by the software team. It is also possible to generate the whole system executable. This means that into the models the peripheral blocks are included. Out of the target-specific system models, the whole executable can be generated. We are going to see this approach in the third part of our webinar, where Christoph is going to generate the whole system executable, which is going to run on the Microchip MCU in order to spin the motor. The in and out blocks for Microchip MCUs are provided by Microchip. Processor-in-the-loop testing proves functional equivalence between model and executed code. Code profiling analysis provides execution time on target processors. This helps to guarantee sufficient performance and helps to choose the right hardware design for a specific algorithm. An executable containing the algorithm and the communication is generated and executed on the target. With the help of target communication, via serial or Ethernet communication channel, the inputs and outputs and execution timing is synchronized between the host computer and the target at each time step. The execution history compares the results of the run in the simulation versus on the target. It analyzes the code coverage and profiles the execution timing. Embedded Coder offers built-in support for AUTOSAR and ASAP2 software standards. It also provides traceability reports, code interface documentation, and automated software verification to support DOE 178, IEC 61508, and ISO 26262 software development. Now we are going to have a deeper look into the example we showed in the beginning. Christoph, Can you show us the closed-loop simulation, the code generation, and the rapid prototyping and debugging with the real motor hardware?
Sure, Daniel. Let's look at the model. The model you see on the screen is a Simulink model of our physical system. It contains the motor, the load, and the control algorithm. And we will start with the full closed-loop simulation. The simulation shows an alignment of the PMSM motor, a forced startup, and the switch over to the closed-loop sensorless control using a PLL observer. We can use the tools to look into the details of the signals. And on the screen we see voltages, currents, positions, speeds, and D and Q currents of the motor. Once you are happy with your simulation, you have to add the peripheral blocks. The peripheral blocks are the linkage between the algorithm in Simulink and the peripheral on the target microcontroller. On the top level here we have the PWM peripheral block, and if you double click on the block you get into the possible configurations for this peripheral. You can do all the required settings to adjust your PWM module for the needs of the motor control algorithm. Another very important peripheral is the A to D converter, which we have in here. Also here you can do all the configuration with the nice pull down menus, and the very important part is that the peripherals for the Microchip microcontrollers are very close linked together, and the PWM module triggers the A to D converter directly in hardware and no software overhead is required. Once you have added all peripheral blocks, you simply press on the build button and code is generated, compiled, and automatically programmed onto the target. Additionally, a code generation report is generated and you get an overview about all the details about the generated code. You can look at the C and header files, and there is also a linkage between the block and the generated C code available. When the target is programmed, the motor can be started by simply pressing the button. To view the signals in the algorithm, you can use the Microchip Pick GUI. On the screen here you can see different signals like phase currents, speeds, and an FFT generated on one of the and an FFT calculated on one of the phase currents. With the potentiometer on the board, you can also vary the speed.
So now we have seen how simple motor control can be. First, you start with simulating your complete system in Simulink, including the motor and the load, and with the single button press, you generate code, you compile it, and you program it onto the hardware. And once the motor is running on the hardware, you can validate with our online debugging tools your motor control algorithm. Recently, we have added CAN and LIN support. We are using the certified IHR LIN stack, and together with the K2L analyzer tools, you can have a nice automotive bus system solution. We are also supporting the DMCLV demo board and the included DE2 communication, which is an additional UART communication with the MOSFET driver. We also support sensorless startup, single shunt for the PMSM motor. Additionally, we can support the Simulink external mode and processor in the loop, so you can verify if the simulation is exactly the same as the code generated for the microcontroller.
Thank you, Christoph, for the presentation. This is a very straightforward development of a motor control algorithm, and the debugging helps a lot with any kind of problems which typically arise during development. We have reached the end of the webinar. As a summary, the 3 key takeaways. In our proposed workflow, the model is at the center. This means that the whole algorithm design is done in Simulink. Any changes during the development process have to be reflected in the model. Out of the model, we generate customized code for Microchip MCUs. The algorithms which we designed in Simulink are directly tested on a Microchip MCU with real hardware using rapid prototyping. Now we are looking forward to your questions and comments. Please type them directly into the Q&A panel. Thank you.